Hello and welcome back to another Codesmith workshop. I'm super excited to talk to you all about promises, asynchronicity, and the event loop. This is part of our JavaScript The Hard Part series, and it's definitely one of our more advanced workshops. If this is the first workshop that you're attending, awesome. I'm excited to have you here. I would definitely recommend that you check out some of our additional JavaScript The Hard Parts workshops as well, but stick around for this one. I would say this is probably the most advanced of our workshops. We're going to be getting into some interesting topics, specifically asynchronicity in JavaScript and how promises make that possible, as well as the event loop and all the different characteristics that come with asynchronicity in JavaScript, like different types of queues and functionality that comes to us through the web browser features or through Node's libuv features. So while we are going to be talking about these rather advanced topics this evening, what we're going to start with are some principles. And the reason why we're starting with these principles, spoiler alert, there is no asynchronicity on the slide here. The reason why we're starting with these principles and these foundational pieces is because understanding these and having a shared vocabulary and a shared diagramming practice for these foundational pieces will help us dive into something a little bit more advanced, like understanding how asynchronicity can work, given that JavaScript is single-threaded and synchronous. So the principles that we're going to focus on, these foundational pieces, are functions. We know that functions are sets of instructions that we can run over and over and over again. We have a function definition here on the screen. When we define a function, JavaScript knows to wrap that code up and have it ready for when we might invoke that function at a later time. So functions are incredibly important. They help us keep our code dry, keep us from repeating ourselves. And they are particularly key when we are talking about asynchronicity. We are also going to be referencing the thread of execution throughout this workshop. The thread of execution is going to keep track of where in the code JavaScript is executing. Which execution context is it in on the call stack? Which line of code is it running and executing at this point? And we're going to use this to think about what we expect to happen and what's actually going to happen based on what we know and how asynchronicity is managed in JavaScript. Of course, memory is a foundational concept as well. When we're working in JavaScript, we know that JavaScript has a variable environment, a place where it can store labels and data associated with those labels so that we can retrieve them in the code and use them to execute code and continue to compute code. So we are going to take this block of code here, which again has no asynchronous functionality in it, and we're going to walk through it line by line as if we were JavaScript. This is our diagramming practice here at Codesmith. By doing this, we will build our foundational for communication, for technical communication, and for understanding as we get into the nitty-gritty of asynchronicity. So I'm going to use, I'm going to walk through this code as if I were JavaScript. So line by line, left to right, top to bottom. And I would encourage you to do the same. So if you are watching this alone or even with others, I would recommend that you walk through this code before you hear me do it and get your own practice in for your own technical communication. So again, the goal of this is to walk through this code as if JavaScript would and get an understanding of how things are happening under the hood so we can make predictions about how JavaScript will handle the code that we write. We have a few things set up in our diagram. We have our global execution context where JavaScript can execute code. We can also see that as the execution context at the bottom of our call stack. Our thread of execution, which I've abbreviated here, is going to start in our global execution context. And as we open different function level execution contexts, it will weave its way into those as they are pushed to the call stack. We have that variable environment as well, represented via our global memory. We'll look at how we get a function level memory as we open up execution contexts. But let's go ahead and walk through this. So the first thing that we're going to do is right here on this first line, we're going to declare a constant with the label num in global memory and set its value equal to 3. So global memory has a label num whose value is the number 3. JavaScript has run this line, so it's going to move on to this next line. And what's happening on this line? Well, we're declaring a function with the label multiply by 2. We're still in the global execution context, as we can see from our thread of execution. So this is going to be stored in the global memory as well. So we have our label multiply by 2, and its value is this function definition. Remember, JavaScript isn't going to execute any of this code at this point. It's just going to wrap this code up in a function definition, ready to be executed later. In our diagramming practice, we represent functions as this symbol here, this box with an F in it, where we can put some input in and get some input out based on the code that we have inside. So this means that JavaScript has run all of this code, and we can move on to the next line. Where do you think the next line is? What do you think JavaScript's going to do next? Well, we're going straight on down to this line, because remember, we're not executing any of this code yet. We're just storing it. What's happening on this line? We're declaring a constant with the label output, and thread of execution still in global memory, so that is where this label is going to live. Output is going to be equal to the evaluated result of invoking multiply by 2 and passing in the argument num. So let's break this down even further, because remember, JavaScript moves from left to right. So when JavaScript sees this label, the first thing it's going to do is check its memory to see if it has a label associated with, or has a value associated with this label, and it does. The value of this label is a function definition, and we are subsequently invoking that function definition. So we're not just accessing the definition, we're actually invoking the definition, and we're passing in an argument, and the argument is num. And again, JavaScript does not know what num is. It must check its memory to find out. In its memory, num is equal to the number 3. So ultimately what this means is that we're going to invoke a local execution context, or we're going to invoke a function and open a local execution context. And just bear with me while I draw this out. We have our local execution context, which comes with its own local memory. You can also refer to this as a function level execution context. And specifically, this is going to correspond to the invocation of the function multiply by 2 with the argument 3, because as we said, num equals 3. So this is our diagram, right? And we are also going to push a stack frame, which you can think of this, as our local execution context, but also the contents of a stack frame, onto our call stack. So let's do that. We have multiply by 2 with the argument 3. This has been invoked. We need to execute it. This means that our thread of execution is going to weave its way in to this execution context. So anything that we define while the thread of execution is pointing at this execution context will be defined in that execution context memory. So let's look at that function and see what's happening. Whenever we open up a local execution context, there's one thing that we're going to do right off the bat, and that is pair our parameters and our arguments. In this case, our parameter is input number. You can think of a parameter as a placeholder in a function for an actual value that we don't yet know. So input number is our parameter. This will be our label in our local environment. And what will the actual value be? What will input number be paired with? What is the argument that we've passed in? Well, it is the number 3. Okay, so in this context, input number is the number 3. So anytime that JavaScript sees input number in this function definition, it will be able to know that in this context, in this scenario, that is equal to the number 3. So we've paired our parameters and our arguments. We can go ahead and move into the first line of the function definition, where we are declaring a constant with the label results and setting its value equal to input number times 2. Let's start with the first half of that line. we're declaring a constant with the label result. Where are we declaring this? Well, our thread of execution is in multiply by 2. This is the execution context that we're currently executing in. So result is going to be stored in that local memory. What is result going to equal? It's going to be equal to input number times 2. JavaScript does not know what input number is, so it will check its local memory and find input number is the number 3. What is 3 times 2? That is 6. So result is the number 6. So JavaScript has executed this first line of its function definition. On to the next. We are going to return result. What is result? Result is the number 6. So the number 6 is going to be returned as the evaluated result of this function, right? Remember, this is the line that we were trying to figure out. What does multiply by 2 with the argument num, or 3, evaluate to? It evaluates to the number 6. So we're going to take that number 6 and we're going to return it to the call site where our function was invoked. So a few things happen when we finish executing the code that there is to execute within a function definition. One of the things that happens is that our local execution context is eligible for garbage collection. JavaScript doesn't have to remember this anymore. It doesn't have to allocate its resources to remembering what this was because it is done. Okay, those resources can be freed up for other things. What else happens? It gets popped off the call stack. And I'm just going to cross this out here for our own ability to kind of go back and re-reference these things throughout our diagram. But just to be clear, this is gone from the call stack. JavaScript doesn't retain it in any way. And this also means our thread of execution weaves its way back into the next frame on the call stack, which is the global execution context. So it's down to execute code in the global execution context once again. So again, JavaScript has no memory of this at all. So when it gets to the next line, it is starting fresh. So let's look at this. We are now going to declare a constant with the label new output. Thread of execution is in global, so we'll be doing this in the global memory. And what is the value of this label new output? It's going to be the value of invoking the function multiply by 2 with the argument 10. So again, we cannot reuse this execution context. It was garbage collected. So instead, we're going to make a brand new execution context and go through the same steps that we just went through. So let's do that. Multiply by 2 is the function definition. We are invoking that function definition with the argument of 10. Let's open a local execution context so that we can execute this code. Okay, so a couple of things. One, I'm going to abbreviate local execution context here. So whenever you see LEC, that is what that stands for. I'm also going to abbreviate local memory. What else do we need to do in our diagram to understand what's going on here? What is JavaScript doing behind the scenes? Well, the stack frame is getting pushed onto the call stack, so let's reflect that here. Multiply by 2 with the argument 10 is on the call stack, and our thread of execution weaves its way inside. What is the first thing that we do when we open an execution context? What do we pair? We pair our parameters and our arguments. So in this case, we have one parameter. It is input number. And the argument that's associated with input number is what? What should the value of input number be in this context? It should be the argument 10. So input number is the number 10 in this context. So we've paired our parameters and arguments. We can move on to the next line where we're going to declare a constant with the label result and assign it to input number times 2. So first, let's declare that constant. What is input number? Input number is 10. What is 10 times 2? 10 times 2 is 20. So result in this context will be 20. What are we going to do with this? We've calculated this first line. We can move on to the next line where we will return result. What is result? Result is 20. Where are we returning it to? Remember, we were trying to evaluate the result of this function invocation. So we will return it here to this label, new output, in global memory. So new output is going to be equal to 20. This is the evaluated result of the function invocation multiplied by 2 with the argument 10. Okay, let's clean up. What happens to our local execution context? It is marked as eligible for garbage collection. What happens to our stack frame on the call stack? It is popped off the call stack. What does that mean for our thread of execution? It weaves its way back into the next execution context on the stack, which in this case is global. And that's it. We've run all the code that there is to run. Our thread of execution is back in the global execution context. There's nothing on the call stack left to run. We also have no synchronous code left to run here. We've gone through all of our code. JavaScript's work is done. So this is the practice that we're really going to lean on over the course of the workshop, and we're going to build upon it as we start to introduce these other pieces that are necessary for asynchronicity in JavaScript. Also, if you've not been to another Codesmith workshop yet, we use the same practice in every one of our workshops, and it's really great to practice yourself and practice your own technical communication. So make sure to do that aloud and do that with others. So those are our foundational concepts: functions, thread of execution, memory. We also looked at the execution context, the call stack as well. But we're going to really be focusing on asynchronicity this evening and how it's possible in JavaScript. To be truthful, asynchronous JavaScript is really responsible for the way that we experience the internet today, and responsible for our expectations of the internet. We expect websites to be fast, and websites can be fast because we can run code asynchronously through these mechanisms that we have available to us via JavaScript. So let's just do a little thought experiment, a little imagining for a moment. First step of imagination: imagine X was still called Twitter and tweets were still called tweets. Are they still called tweets? I'm not sure. But imagine that we are going to twitter.com, and when you go to a website, what happens is that you're actually sending a request to the computer that holds the code, that holds the data, or some set of computers that holds the code and data that is necessary in order to render that website. So we send a request to twitter.com. Specifically, we send a request for the first tweet from a user called Will. And we're doing a little bit of hand waving here. This is not a function that exists in JavaScript. We would have had to implement this somewhere. But the output of this function should be that we get Will's first tweet. And the evaluated result of this should be stored in a constant with the label tweets. So if the content of the first tweet is the string Hiya, then tweets would have the value of Hiya. So before we move on to the rest of this, let's just focus in on these characteristics of JavaScript that are important to understand. JavaScript is single-threaded. This means one command is running at a time. JavaScript is not doing more than one thing at a time. It is single-threaded. And we saw that. We have one thread of execution, okay? Also, JavaScript is synchronously executed. So each line is run in order. JavaScript doesn't move on to the next line until it's finished executing the line before. So in this case, when we are invoking getTweets and we're sending a request to a server, to a computer that Twitter manages, this is going to take some time. There's going to be some latency involved in this. In our example, we're saying that it's going to take 350 milliseconds of wait time to get this evaluated result from this function invocation. Okay, 350 milliseconds is not that long when we think about it, but it is really long when we are working in web development. So while we think that this is, yes, a split second, wait times like this can really add up when you're dealing with hundreds of requests. And that is what's happening when you're loading a web page. You're not just sending one request to twitter.com/will/1. You're also getting resources to load images. You're getting resources to make sure that you're authenticated to log in and access the resource that you're asking for, getting resources for ads and these types of things. So, and I'd encourage you to go to a website, open the network tab in your browser DevTools, and look at how many requests happen when you load a website for the first time. In that world, 350 milliseconds is a lifetime. And so the problem with this is if we are asking for the tweet from Twitter's server or the computer that holds this information, and it can take a long time, there might be some other code that's completely unrelated to displaying our tweets, to using this constant that we want to be able to execute. But because JavaScript is single-threaded and because it is synchronously executed, we will have to wait in order to do that. Okay, so how can we get around this? How can we get around the fact that no code can run in the meantime? Okay, this is where one of our extra features comes into play. Maybe you have heard of a function called set timeout. Okay, so I know I'm kind of what is the word? Leaving you on the edge? No, I can't think of it. It doesn't matter. Well, we'll come back to this. We'll come back to this. I promise that this is related. Okay, so set timeout is a built-in function, right? We don't define this function. It comes to us with JavaScript, with the web browser. And it takes two arguments. The first argument is a function definition, right? It's a function definition, and it's how we're sending this function definition to a timeout for a certain number of milliseconds. And we're essentially saying we don't want to invoke this function definition until this number of milliseconds has passed. Okay, so knowing what we know of JavaScript, take a look at this code. Feel free to pause the video and take a look and take a guess. What do you think is going to log to the console first? Will it be this console log with the string me first, or will it be this console log with the string hello? Okay, take a moment, think about it, and truly make a guess before you hear the answer. Okay, before I tell you the answer, one thing I want to emphasize, and this is really important when it comes to engineering, is that when you're learning, there are no bad guesses. There are wrong answers, but there are no bad guesses. So even if you guess and you guess the wrong answer, guessing is part of the learning process. So I implore you one more time before I reveal the answer. If you haven't made a guess yet, please do that now. The first log that we're going to see logged to the console is me first. It has nothing to do with the contents of the string saying me first, but that was a little bit of a hint. The second log that we'll see is hello. And if we think about this, perhaps it makes sense, right? We are telling JavaScript, I don't want to run this function definition yet. I want to wait for a second before I run it. And I want to run this first. Perhaps your guess was the opposite. Perhaps you guessed that we would first define this function, and then we would invoke this function, and we would wait 1,000 seconds, and then we would run print hello and console log hello, and then we would console log me first. So how is it that we're able to do this? It is because of the web browser API. Because when we use a function like set timeout, we are sending this function definition and this unit of time, or this number, to the web browser API to keep track of. Only after 1,000 milliseconds will the web browser API queue up this function to be added back to the call stack at some point. Okay, so digest that a little bit. We're going to get further into the details in a moment, I promise. But get ready to guess again, because I have another question for you. So this code is nearly identical to what we just looked at. The distinction is that our second argument to the setTimeout function is not 1,000 milliseconds, it is 0. So given this, and what we just spoke about, and what you know of JavaScript, what do you think the order of the console logs will be in this case? I'm just going to give you a few seconds to come up with your guess. Feel free to pause the video if you need more time. Okay, so if you guessed me first will log to the console first, your guess is also the correct answer. If you guessed hello would log to the console first, I can understand why, right? We're saying wait 0 milliseconds. Don't wait at all until print hello should be ready to be invoked. But there are more things happening behind the scenes that we haven't yet talked about in our diagramming, and we're going to do that right now. So setTimeout, as I said, is a built-in function, and it gives us access to some additional functionality that we don't have access to otherwise when we're just running JavaScript by itself. So we talked about JavaScript, the foundational, the fundamental pieces that we need, and we've been including in our diagram, the thread of execution, the variable environment, JavaScript's memory, as well as the call stack. But we're going to add in some additional components here. So one of those things, and we're going to focus on front-end JavaScript for now and on the web browser. One of those things is the web browser APIs. So functionality that is available to us when we run JavaScript in the browser. When we're running JavaScript on the backend in something like Node.js, for example, we also have access to these features, but they're not coming from the web browser anymore. You might hear this referred to as background threads, or you might hear people throw around the library libuv. When it comes to asynchronicity on the backend, we're going to focus on the web browser APIs for the purposes of this lecture and this workshop, but the same sort of functionality is available on the backend in JavaScript as well. So when we're talking about the setTimeout function, we are going to use that to make use of the web browser APIs. Some additional pieces, and we'll get to some of these sooner than others, are promises and a couple of queues, the callback or the task queue, as well as the microtask queue. And really the star of the show here is the event loop, who is responsible for coordinating getting functionality that was processed elsewhere and held elsewhere back to the call stack. And that is the event loop. So we are going to take a look at this one more time, and we're going to diagram it out. Okay, so callback functions. We have a whole workshop on callback functions and higher order functions. I really encourage you to watch it if you haven't already, or attend one of our live workshops. Callback functions are functions that are passed to other functions as an argument. So print hello, which is a function definition, is a callback function because we are passing it as an argument to setTimeout. Okay. All right, let's dive into the diagram. So a couple things to notice. I've added some more pieces to our diagram. Of course, we have our global execution context, we have our global memory, we have our call stack with the global execution context at the bottom, and we have our thread of execution right there in the global execution context. But I've also added a console since we are going to be logging some things and I want somewhere to capture it. I've added a box for the web browser API. You can think of this as functionality that's available to us through something like Chrome or Safari or Edge or something like that. And I've also added the callback queue. You can call this a callback queue or the task queue. Okay, let's go through this code as if we were JavaScript, line by line, and get a sense of what's happening here. And I'll zoom in a little bit so that it's nice and big for y'all. Okay, so JavaScript starts on line 1. What is the first thing that it does? It is going to define a function with the label print hello. And where is it going to define this? Well, we are in the global memory, so that is where it will be defined. And what is the value of print hello? Well, it is a function definition. JavaScript isn't invoking this code yet. It is just wrapping it up and storing it so that it is available to be invoked later when we reference it. So what is the next line that JavaScript is going to go to from here? Well, we've wrapped all this up in the function definition. So our next line of executable code is line 5, where we are invoking a function setTimeout with 2 arguments, print hello and 1000. We're invoking a function, so this means we need to open up a local execution context. So let's do that. What is the name of the function that we are invoking? It is setTimeout with the arguments print hello and the number 1000. So when we are invoking a function that we have defined, we can find that in the memory, in the variable environment. We can find the function definition itself. But remember, setTimeout comes built in. We have access to this through JavaScript and the browser. Here's our local execution context. And so what that means is that we're not going to see this in our diagram here. So we're going to make some assumptions about what the parameters for this function definition might be called. But let's first push this invocation onto our call stack. I'm going to abbreviate some things here just for the sake of space. And we'll weave our thread of execution inside, because this is now where JavaScript is going to be executing code. And again, we don't see the function definition here, but I can invite you to trust me that setTimeout is going to do a few things. The first thing that we're going to do, just like any other function, is pair parameters and arguments. So again, we don't know the parameter labels here, but we can come up with our own labels for the sake of this example. So we said that this function definition takes 2 arguments. The first is a callback, and so we'll call that parameter a callback. And what is this callback? Well, it is the function definition of print hello. Okay, the second argument is going to be a delay in milliseconds, how long we want to wait before this is pushed to the call stack. And in this case, our second argument paired with the parameter delay is 1000, the number 1000. So what happens, what's executing here is that setTimeout is going to use its function definition to take the first argument that we've passed in, the callback, and the second argument, and pass it off to the web browser API. So what this means is that print hello, the print hello callback function, and the 1000 milliseconds, the number 1000, will be sent over to the web browser API, which will receive this and start a timer. Start a timer at 1000. And once that timer reaches 0, it will know that it's time to do something with print hello. But in the meantime, setTimeout has done its job. It is finished executing. There's no executable code left to run. So we can do our normal cleanup, set it as eligible for garbage collection. We can pop it off of the call stack, and we can move our thread of execution back into the next stack on the next frame on the call stack, which is global. Okay, so JavaScript has finished executing this code. We haven't yet executed this function definition, but we have started. And maybe in that time, the timer has started to tick down. Okay, what happens next? JavaScript has executed line 5. What is the next line of executable code? We have line 7. We're going to console log me first. So let's do that. And in that time, maybe our timer has gone down further. we have run all of the code that is left to run here, which is great. There's no code that we're waiting on, that we're still running, that we're still executing. And meanwhile, the browser continues to keep track of the timer until it gets to 0. So once we are at 0 milliseconds, what do you think happens? Where do you think this callback function, this function definition, goes? This callback function is going to go into a queue, specifically the callback queue, the task queue. So once the timer reaches 0, this is sent over to our queue. You can think of a queue differently than a stack, where a stack is last in, first out. Let's mark this here. Last in, first out, LIFO. A queue is first in, first out. That's just like a line, right? If you are standing in line, you don't want the person at the end of the line to go first, right? It's the person at the beginning of the line who should be next. And the same is true for queues here in JavaScript. Okay, so this is, again, it's a function definition, hasn't been invoked. So how is it going to get from the queue to the call stack, where we can move our thread of execution inside and execute the code within this function definition? Well, the answer to that is the event loop. So I said a few minutes ago that the event loop is responsible for coordinating all of this when we're working in an asynchronous world. The event loop is checking a couple things, and it really is a loop. And so you can think of these things that it's checking as what it's looping over. The first thing it's checking is the call stack empty? And in this case, is the call stack empty? It is, right? It's empty. We're back in global. There's nothing else left to run. And that is the second thing it's checking. Is there any synchronous code left to run? And if either of these things, let me rephrase that. If the call stack is empty and there is no synchronous code left to run, then the event loop knows that the queue can move this functionality to the call stack. So we can take print hello, take it to the call stack and invoke it, because there's nothing else on the call stack and there's no synchronous code left to run. There's nothing after line 7. So because of this, print hello is dequeued and it is invoked on the call stack. And again, this is a function invocation, which means we need to open up what? A function level execution context or local execution context, so that JavaScript can execute the code within print hello. So print hello is on the call stack. The thread of execution has woven its way inside, and we are ready to pair our parameters and our arguments in this local execution context for print hello. One thing to note is in this function definition, there are no parameters and there are no arguments. So even though JavaScript will check to see if there's anything to pair there, there's nothing for us to take care of in our diagram. So we can go straight on into the first line of the function definition. And what are we going to do here? We're going to console log hello. Okay, so we've console logged hello. There's no code left to run in this function definition. So we can do our usual cleanup, mark this context as eligible for garbage collection, pop it off the call stack, and weave the thread of execution back into the stack frame below this on the call stack, which in this case is global. And we have run all of our code and we've done something asynchronously. We've passed some code off to the web browser API, started a timer, and once that timer was up, the web browser API pushed that to our callback queue to await two things. One, that the call stack is empty, and two, that all the synchronous code has run. And once both of those things are true, the event loop, and let's just create this little cycle here. The event loop will take our callback function from the callback queue, push it to the call stack, and invoke it. Okay, so the event loop is super important. This is how we are synchronizing, how we are coordinating this asynchronous functionality in JavaScript, which again is a single-threaded synchronous language. This is a lot to take in, so take a moment and think about these things. What did you expect to be logged to the console first? And how was hello logged to the console at all, right? There was a journey that it went through. Print hello was passed to set timeout. The function definition went and sat in the web browser API for 1,000 milliseconds. Then it went to the callback queue, and only when the event loop deemed it was time was it sent to the call stack and invoked. Take a moment to absorb this, and then we are going to look at this next example with that 0 milliseconds. Remember what we said about the order that we are going to expect here. That me first is going to log first, and print hello's console log output of hello will log second, even though this is 0. Given what we just looked at, why do you think that is? Take a moment to think about it, and then we will diagram it out. Okay, let's do it. So again, we're walking through this code as if we were JavaScript, following all the JavaScript rules that it knows about. So first line, we are declaring a function. Where are we declaring this? Well, a thread of execution is in the global execution context. We're going to declare this in the global memory. And what is this? What is the value associated with print hello? The value associated with it is a function definition. We're not executing the code inside this function definition at the moment. We're storing it, preparing it, readying it to be executed later whenever it's needed. So where's the next line of executable code for JavaScript? It is line 5, where we're declaring another function. Where are we declaring this? In the global execution context. That's where our thread is at the moment. So let's declare block for 1 sec. Again, this is also a function definition, so we're not invoking it right now. One note I want to mention about this is that this is a synchronous function. It is not asynchronous, where we don't care the contents of this function. We just know that it takes a long time to execute. Okay? What is the next line of executable code? The next line of executable code is line 9, where we're invoking the built-in function set timeout, passing in 2 arguments, print hello and 0. We're executing a function, so we know that we need to open up an execution context. Okay, we did not define set timeout. It comes to us built in. It's available via the browser. So we aren't going to go through the details of how this is executing, but we will do the things that we normally do when we open up an execution context. We'll make sure that we've pushed this to the call stack. And again, I'm going to abbreviate some of this for the sake of space. We'll weave our thread of execution into this execution context. And we will pair our parameters and our arguments. Our parameter here, we'll call our first parameter callback, and it will be paired with the argument print hello. Our second parameter we can call delay, and it will be paired with the argument 0. what is the functionality of setTimeout at a high level? setTimeout is going to pass these arguments to the web browser API. So print hello, and our timer, our delay of 0 is going to the web browser API. The web browser API is going to start the timer. And once the timer reaches 0, what's going to happen? So we passed in 0, so immediately our timer is going to expire. And what does the web browser do with our callback function? It's going to take it and send it to our callback queue. So let's do that. Our timer has expired, so we'll cross that out. Okay, think back to what the rules are for the event loop. What is the event loop checking? How does the event loop know when it can send functionality from the callback queue to the call stack? The first thing it's checking is the call stack empty? And at this exact moment, is the call stack empty? No, it is not. We haven't even garbage collected setTimeout yet. So we don't even have to ask the second question. The first question is false. We cannot push anything from the callback queue while the call stack is not empty. So let's go back and continue to run our JavaScript code synchronously. First, we can start with garbage collecting setTimeout, popping it off the call stack, weaving our thread of execution back into global. Just put it in here for now. And at this point, at this very exact moment, the call stack is empty, right? Great. Has all of the synchronous code run? It hasn't. We've just completed line 9, and there's more synchronous code to run. So the event loop cannot yet push print hello onto the call stack. What's the next line of executable code? It is this function invocation. Excuse me. So what is print for 1 second, block for 1 second? Block for 1 second is a function definition that we are going to invoke. We're invoking a function, which means that we will open up a local execution context in order to evaluate this code. Let's do that. And again, this is just for the sake of our example. We don't have knowledge of what block for 1 second is or the functionality inside of it, but this is just meant to show that a lot of time, relatively a lot of time, can elapse before things get back from the callback queue to the call stack. Let's push this onto the call stack, and we will weave our thread of execution inside, and time elapses, right? Whatever is inside the synchronous function, it takes a long time to run, and 1 second later, 1,000 milliseconds later, it has run, and we can garbage collect it. If the browser was still keeping time of how much time had elapsed since it received the print hello callback and started its timer at 0, the time would be over 1,000 milliseconds, right? Because we blocked for a second, we've run a couple other things, and yet our callback queue is still holding on to print hello. And that's because of those 2 rules that we spoke about. The event loop is still checking. Every millisecond it's checking. It's a little bit tedious in that way, right? So it is checking, right? Even right now, as we block for 1 second, is the call stack empty? No, it is not. Okay, we cannot do anything with this yet. But once we do garbage collect and pop this off the call stack and weave our thread of execution back into global, the event loop finds that the call stack is empty. Hooray, it goes on to its next question. Has all the synchronous code run? And has all the synchronous code run? No, it has not. We still have a console log left to run. So it's not time yet for print hello to make its way to the call stack. Let's move on to the next line in the synchronous code in JavaScript. We're going to console log me first. So let's do that. Now JavaScript will check, or rather, the event loop will check. Is the call stack empty? Yes, it is. Has all of the synchronous code run? Yes, it has. We have made it to the bottom of the file. And so what does this mean for our callback queue? It means that we can dequeue from our callback queue and send it to the call stack. So print hello, let's do this. Print hello is pushed to the call stack, invoked. We are invoking an execution context, which means what? Well, we have to open up a local execution context. Bear with me one moment while I shrink our previous execution context. Remember, these are garbage collected, so JavaScript doesn't even have to save space for these. We're saving it for the sake of our diagram. But let's open up our local execution context for print hello for this function definition. Notice how it functions just like every other function invocation once it's pushed to the call stack, right? It went through a different path in order to get to the call stack via the web browser API and the callback queue. But ultimately, print hello is a regular old function, and we're going to handle it in the same way that we do all other functions once it's on the call stack. Are there any parameters and arguments to pair? No, there are not. So we'll move on to the first line in this function, which is console logging hello. So let's do that. And I'm realizing, and maybe you caught me, that we did not weave the thread of execution into print hello, but indeed that does happen, right? Because we cannot execute code where our thread of execution is not in JavaScript. So we've printed hello, and that is all the code in this function definition. So we do our normal cleanup. We mark print hello as eligible for garbage collection. We pop it off the call stack. The thread of execution weaves its way back into global, and we are done, right? The event loop doesn't have anything to check because there's nothing in the queue. Isn't this interesting? Despite our timer being set, despite our delay being 0 and our web browser setting a timer that immediately goes off and immediately pushes our function definition, our callback function, into our callback queue, it is not until over 1,000 milliseconds later that that functionality is actually put on the call stack. This is why we still see me first logged first, because print hello went through an asynchronous flow. This is super interesting. And while the order of console logs might not feel like a super real world example, it's a really useful way to understand how things are moving through a flow or not when we are working with asynchronicity. We can add console logs and look at their order in the console to verify that what we expect, the order that we expect, is what is happening or not, and then investigate why. Okay, so y'all, this is asynchronicity in JavaScript at work. We have used the event loop to coordinate functionality from our callback queue getting to the call stack. We have made use of the web browser API for some of its functionality, like a timer, for example. And we've been able to, in JavaScript, write some asynchronous functionality. And this is pretty exciting. And this is really kind of the beginnings of what is able to make our websites very dynamic and really set our expectations high in terms of how quickly we expect websites to load and to be able to load a list of tweets and all these other pieces. So let's talk about some of the benefits and the challenges that come with this method, come with the callback method, right? So one of the challenges that comes with this is that our callbacks, when we're thinking of things that are the complex websites that we use every day, our callbacks can become very nested. There is no nesting of our callbacks in this example of code, but if you were to look at and Google the term callback hell, you would get a sense of what this means. And again, this is for illustrative purposes, and it's fairly simple. But as we get more and more complex and we want our websites to do more and more things, we can really make it difficult for ourselves as engineers to reason about what's going on and to maintain that code and add to it. And maybe for you, it feels a little bit weird to think of passing a function definition into another function as an argument and not have it run right away. Like, how come this doesn't immediately get to the call stack? Well, we saw why, because it's going through a different mechanism through the web browser API and the callback queue. So maybe at this point, it is a little weird to think about that semantically. But once you understand how this works, it is super explicit to understand what order things should happen in, okay? And so this is definitely an improvement on not having the ability to do this. But we're going to dive into an additional and more modern way to deal with asynchronicity in JavaScript. And that is a solution that comes with ES6. I know on a previous slide we saw ES5. ES stands for ECMAScript. ES6 comes to us in 2015. It's really the first big update. Maybe ES5 is the first big update, but it's an update to JavaScript, right? JavaScript was created in the 90s, and between the mid 90s and even 2015, a lot has happened on the web. I'm sure we all can agree. And so the ability and the capabilities of JavaScript had to be improved and expanded. And so in ECMAScript 6, we are gifted the feature of promises. Promises are two-pronged facade functions that are going to allow us to hook into some web browser capabilities where we'll be able to start up some worker threads that are outside of JavaScript they're initiated by the web browser and progress that functionality there. And also they return immediately a placeholder object. We call this the promise object. And because this is returned immediately, we are able to move on in our code synchronously as we expect that we can in JavaScript. So we are going to diagram through this in a moment, but before we do that, I want to talk through a couple things. First, I want to just briefly touch on the fetch function, which is now built into JavaScript. We can use this without defining it ourselves, thankfully. And this is a promise-based function. It returns a promise. And then I want to talk about the promise object a little bit. So let's start by talking about the fetch function and the code that we're seeing here on the screen. So first of all, nothing new here. We're defining a function. We're giving it a label display. We're wrapping its function definition up into global memory associated with this label, and we'll be able to use it later, right? This next line, there's something a little bit different happening here. So this is not new. We're declaring a constant with a label. The label is future data. But we are setting it equal to the evaluated result of invoking fetch with the argument twitter.com/will/tweet/1. Again, we're still trying to get that first tweet from a user called Will. Okay, so fetch returns a promise object, and we're going to look at the structure of that object in a moment. Objects, as we know, can use dot notation. So future data is going to resolve to an object. And on the next line, and we can move on immediately to the next line because this function immediately returns a promise object. On the next line, we are using dot notation to access a function on this object called then and pass in an argument display. What is display? Display is this function definition. We're passing in a function definition to this dot then function. One of the things that I love about the promises solution over callbacks is how semantic it is. And this is for us. This is for engineers. This is not for JavaScript. We could, abbreviate all of these down to simple letters and they wouldn't care. When we think about naming and semantics, we're thinking about the engineers who are writing and reading the code and maintaining the code. So without thinking too much about this, I can make a pretty good guess that what's happening in this code is that we're going to fetch the first tweet from Will, and then we're going to display it. This property comes built in as well, and again, very semantically named, so I can quickly reason about what's going to happen once I have the result of my fetch request. We'll look at the object, the promise object a little bit more in a moment. Okay, so we're going to do, we've defined our function display. We have sent a fetch request to get this tweet. And when we have it, we will display it. And then we also have our console log me first. So before we go through our regular diagram, I want to talk a little bit more about this promise object. This promise object has a lot of properties, but we're really going to focus on 3. Maybe we'll call it 3.5 because of .then. The 3 ones that I want to focus on are the keys or properties, value, status, and onFulfilled. Again, we don't have to do anything to create these properties. They will be created automatically whenever we use a promise-based function. So the value, when fetch immediately returns, when it immediately returns, resolves to this object, the value is undefined. We don't yet know what the value is because it takes some time for us to get that value back. The status is going to be one of 3 things. It starts as pending, but it could also be fulfilled, as in the value is now known, or it could be rejected, as in there was an error. We weren't able to get the first tweet of the user will. Okay? We then have this last property that we're really going to focus on here, which is called unfulfilled. And what this is a place for us to store data, or not data, for us to store functionality that we want to run once the status changes to fulfilled. Again, we love the semantics of this, right? Once the status is changed to fulfilled, what will we do? We will go to the onFulfilled property and we will invoke any of the functionality that lives there. So based on the code here, what do you think functionality is going to be stored at onFulfilled? It is whatever we pass in to then. So in this case, that is display. And let's use a different color for this display function. So this is waiting, this function definition is waiting here for the status to change to fulfilled. And then we will use the event loop and the other mechanisms that we talked about to get this to where it needs to be. All right. The promise object, there's a lot more to this, but these are the 3 things that we really need to know in order to understand how this works for our example today. And I really invite you to continue to explore and dive into promises and the promise object and promise chaining after the workshop. Okay, let's diagram this out with all this in mind. One thing I want to point out is that I've added another queue called the microtask queue. So we still have our callback queue, but we've got an additional queue here in our diagram called the microtask queue. You can see our diagram is getting a little crowded. It's getting a little crowded here. Okay, let's walk through this as if we were JavaScript in the same way that we have in all of our other diagrams. The first thing that we're going to do is define a function where in global with the label display. And you know what? I'm going to use a different color for this just so that we can see this move through. Okay, what is display? Display is a function definition. Where is the next line of executable code? It is line 5, where we declare a constant in global memory with the label future data. Let's see, let me get a different color. Okay, future data. And future data is going to be equal to the evaluated result of invoking the fetch function with the argument of this URL. Now remember, fetch returns a promise, and this happens immediately. So even though we don't yet know what the value of the first tweet of our user will is on Twitter, we still have an object that is immediately returned from fetch that at the very minimum has three properties: value, which is currently undefined. We also have status. What is the status currently at this point when our value is not yet known? The status is pending. And what's that third property that we spoke about just a moment ago? The third property is onFulfilled, which is where we can store functionality that we want to run once we get this value back, once the status changes from pending to fulfilled. Okay, so we have run line 6, but let's talk about what is happening, right? Fetch is going to make use of additional worker threads in the web browser. So not only is fetch immediately returning this object, but it's also taking this request to Twitter, and I'm not going to write out the whole URL, but that is just for the sake of abbreviation and space. And it's saying we are making a GET request to this external resource. Web browser, you use some worker threads to take care of that, while JavaScript continues to synchronously run its code. Once the web browser has its answer, where do you think it's going to put that? Where do you think it's going to send the value of the first tweet of Will? It's going to populate our value in a promise object. But right now, it's working on getting that value. And while it's working on that, we can move on in our synchronous JavaScript code to the next line. The next line of executable code is line 8. And this might feel a little bit new, but we're still using the same JavaScript principles that we know about: objects, dot notation, methods, and that we've seen in other practices. So what does JavaScript do on line 8? Checks future data. What is the value of future data? It is an object. It does have a hidden property, a built-in property called then. And when we invoke then on a promise object and pass it an argument, a callback function, what happens is that is going to take that callback function, copy this, and save it within our onFulfilled property. And we can get into the details on what this is, having trouble, but this is as detailed as we're going to get into it for right now. Display is in our onFulfilled property. Okay, that means we have run line 8, we have completed our code there, and we move on to the next line of executable code, which is what? Console log me first. Before, let's say in between, or as we were doing this, Twitter got back the value of the first tweet of our user Will, and the value of that is Haya. Again, where does this value go? This value is going to be stored at the property with the label value. How semantic is that? So the web browser has done its job. Switch my pen color here. The web browser has done its job. It sent a request and received a response. And this also means that our status changes from pending to fulfilled, because we now have a value defined, gotten our response back from our fetch request. So what does this mean? Again, this is all happening in a split second, somewhere in between these two things. What this means is that the onFulfilled functionality that we have specified is going to be passed to a queue and wait its turn to get onto the call stack. Which queue do you think it will be passed to? So this is indeed a callback function, but because it has come through a promise object, it gets priority in the microtask queue. So this is sitting in the microtask queue, and this whole time, our event loop is still coordinating what's going on here, and it's asking the same questions. Is the call stack empty? Has all the synchronous code run? And as I'm saying this, I'm realizing that we did not invoke. We invoked fetch, we talked through it, but we did not diagram through it. So let's just add this for the sake of our diagram. This function execution context, this local execution context, is ultimately how we get this URL, this request to the web browser API. So it is important to know that that happens. And it did move on to the call stack, and the thread moved into this execution context. But as soon as it returns its promise object, we do garbage collect it, right? Just like every other function that we've seen. And our thread of execution moves back into global as we pop this off the call stack. Okay, with all of that said, and our onFulfilled property pushing this to the microtask queue once the status is fulfilled and we have a value Haya. All of that said, the event loop is still checking. Now that it has something in the queue. Is the call stack empty? Yes, it is. There's nothing on it at this moment. Has all the synchronous code run? No, it hasn't. We still have this line of synchronous code on line 11. So we will run that and we will log to the console, me first. And again, the event loop continues to check. Has all of the synchronous code, or excuse me, is the call stack empty? It is. Has all the synchronous code run? It has. So now it can take this display function and push it onto the call stack and invoke it. And here's something that is interesting. When we look at this display function's function definition, we see that it takes an argument. What argument do you think is going to be paired with the parameter data? Take a moment to look around and get a sense of where this might come from. Again, I would encourage you to guess, even if it's the wrong answer. There's no such thing as a bad guess. If you guessed that whatever is associated with the property value in future data would be paired with the parameter data, you are correct. So in this case, value happens to be a string, but value could be an array, it could be an object, it could be any valid data type in JavaScript. And so this is what is passed into the invocation of display. This is a function definition, so let's open up a local execution context, a function level execution context, in order to evaluate this. Let's make sure our thread of execution weaves its way into this execution context. And let's pair our parameters and our arguments in this local memory. So our parameter is data, and our argument is the value Haya, the string Haya. Okay, so when we go into this function definition, what does this do? We are going to console log whatever data is. What is data? In this context, data is Haya. So we will console log the string Haya. There is nothing left to run inside this code, so we will do our regular cleanup. We will mark it as eligible for garbage collection. We will pop it off the call stack. Our thread of execution will weave its way back into global. A couple of things that I want to note. One, when we are using promise-based functionality, we are using the microtask queue. We have a couple queues listed here. These are, in fact, not all of the queues that exist, but these are the ones that are fundamental for us to understand promises and callbacks. Which do you think gets priority with the event loop? So we know the event loop checks the call stack to make sure that it's empty, It makes sure all of the synchronous code is run. When that is true, if there were multiple functions waiting in our queues, which do you think would be pushed to the call stack first? Make a guess, and then we'll talk through the answer in our next diagram. Also, if you need to pause and take a break and kind of absorb what has happened or rewatch what we just did, please feel free to do that. I have folks who come to this workshop multiple times, getting different things out of it each time that they come, and also feeling that a few things elude them each time they come. So that's completely normal. Again, this is one of our more advanced topics. And so if you're feeling a little lost, please don't give up here, right? Continue to make those guesses. Even a guess of the wrong answer is a good guess. Okay, let's move on and talk a little bit more about promises. So, promises come to us via ES6. They are objects. They are special objects in that they follow a particular schema, but they are JavaScript objects, and they are returned immediately when we make a call to a web browser API or feature. In this case, that is fetch, but there are other functions that also return promises. Promises act as this placeholder. This promise object acts as this placeholder for a value that's not yet known when the request is made. And we are going to queue up the functionality that we want to run later using .then. So we'll pass any of our deferred functionality as its function definition into .then so that once we have our value, then we can do something with it. Automatically, behind the scenes, when these functions get pushed to the call stack, the argument associated with their first parameter is going to be the argument of value in our promise object. One thing we haven't talked about here is error handling, which is incredibly important when it comes to promises. We mentioned the rejected status on the promise object, and I'm going to leave that to y'all to dig into further. This is so helpful in terms of figuring out what went wrong when I'm not able to fetch the first tweet of our user Will. Why not? What went wrong? We'll be able to use error handling in order to help us figure that out. Okay. So, as I said, we had a couple queues in our last diagram. Promises go to the microtask queue. But we also have, and it is valid, to use asynchronicity that makes use of the callback queue or the task queue. And we also might have synchronous functionality that takes a long time to run. So when we think about all of these different pieces and we think about how they might be combined together, how will this work with our rules of the event loop and our queues? So we know that the event loop is checking, is the call stack empty? Has all of our synchronous code run? Where does it check next? The next place it checks is the microtask queue empty? And then only if the microtask queue is empty will it push functionality from the callback queue to the call stack. So we've added some additional checks for the event loop. The event loop is very busy. It's checking quite a few things. And so with that in mind, take a look at this code and make a guess as to what order you think we will see the logs in. We have a couple of function definitions here. So again, we're not executing those. We're just defining these functions. One console logs an argument data, or excuse me, a parameter data. One console logs the string hello. Another is a synchronous function that takes a long time to run, 300 milliseconds. So these are all our function definitions. And then we are invoking a few things. We're invoking setTimeout, which we know is a built-in function that we're able to use to access browser features. And we're passing a callback function print hello. We are also declaring a constant future data and making a fetch request. This will immediately return a promise object, which we will then display. We are also invoking A synchronous function, again, block for 300 milliseconds is synchronous, and it's just going to take a long time to run, relatively long at 300 milliseconds. And we're console logging meet first. So there's a lot of console logs here. What do you think the order will be? Let's diagram it and find out. So just as we did in the very first diagram where there was no asynchronicity at all, we're going to walk through this as if we were JavaScript. And we're going to start just where JavaScript starts on line 1. Let's make this a little bit bigger so we can see. So the first thing that JavaScript does with its thread in the global execution context is define a function with the label display in global memory. Set this equal to a function definition. So first line done, we'll move on to the second line here. The next thing we're going to do is define a function with the label print hello in global memory. Okay, we've run these first 2 lines. We move on to the next line. The next thing that we're doing is defining a function with the label block for 300 milliseconds. And this will be a function definition. What is the next line of executable code? Well, it's line 6, where we're going to invoke the built-in function setTimeout, passing it 2 arguments, print hello and 0. So we're invoking a function, which means that we need to open up a function execution context. What are the arguments here? Well, the first one is print hello, which is a function definition, and the second one is 0, the number 0. Let's open this up. We have a few things to put on our screen here, so I'm going to try and leave some space. This is our local execution context with its own local memory. Okay, what's the first thing that we do once we've pushed something to the call stack and weaved our thread of execution inside? The first thing that we're going to do is pair our parameters and our arguments. So our callback parameter will have the value of print hello, and our delay parameter will have the value of the number 0. What does setTimeout do when we execute it? It takes these arguments and it sends them to the web browser API. So here we go, print hello and the number 0. And what does the web browser API do with this? Well, it takes our delay and it starts a timer. Of course, we've passed in 0 milliseconds. So as soon as we reach that, which is immediately, the web browser API is going to take this functionality and send it to where? The microtest queue or the callback queue? The callback queue. We're using setTimeout here. This is from our ES5 functionality, and so we're going to go to the callback queue. Okay, setTimeout, its execution context, is eligible for garbage collection. It's done its job. There's nothing left for it to do. We can garbage collect it, pop it off the call stack, and weave the thread of execution back into the global execution context. Fantastic. Let's move on to the next line of our executable code in JavaScript, line 8, where we're defining a constant in global memory with the label future data. And we're setting it equal to the evaluated result of invoking the fetch function, passing in this URL. So let's do this right this time. We're invoking a function, which means that we need to open up a local execution context. I'm just going to abbreviate this to twitter.com, even though we know the full URL is twitter.com/will/tweets/1. Just for the sake of space, we'll keep it short. And this execution context does just what every other execution context will do. We will move the thread of execution inside it, and we will pair our parameters and our arguments. Again, this has a local memory and a local execution context. And our URL parameter is going to be paired with twitter.com/will/tweet/1. So a couple things happen here. First of all, what fetch is going to do, that the execution is going to do, is take this URL and send the information about the request to the web browser API to get to work on it, to get to work on retrieving the tweet that we are looking for based on this URL. So let's do that. We'll send this to the web browser API, which is going to get its worker threads started on retrieving, on getting this tweet. The thing that fetch is going to return is a promise object. Okay, and we know that the promise object comes with a few properties. Value, which right now, undefined. We don't yet know what this will be. What is status currently? Currently, status is pending. And what is unfulfilled currently? Currently, unfulfilled is empty. But fetch has returned. And just like when we return from any other function, that means that this execution context is eligible for garbage collection. We can pop it off the call stack, and we can weave the thread of execution back into the next frame on the call stack, which is global. What is our next line of executable code? We have line 11, a function invocation of block for 300 milliseconds. So let's push this to the call stack. And open up an execution context to evaluate it. Okay, the contents of this function definition are not important. What is important is that it's a long executing function. There's a lot going on in there, whatever it might be, and it is synchronous code, but it's going to take a while. So what is important to know right now is that print hello, even though its timer was 0, is still in the callback queue. Let's say during this 300 milliseconds, let's say, I don't know, 100 milliseconds has passed, and let's not forget our thread of execution is in this new execution context. But let's say 100 milliseconds has passed, and in that time, the web browser has gotten the first tweet. Okay, so what happens at that moment is that our value is updated. It goes from being undefined to being the value of the first tweet, which we know by now is the string Haya. Okay, this also means our status updates from pending to unfulfilled. Oh, you know what, y'all? We skipped a line. And it's important to get this right, so we are going to go back and make sure that we diagram through this as we should. Okay, so let's go all the way back and make sure that we've got this right. Okay, so our next line, after we have moved our thread back into global, after we've garbage collected fetch, our next line of executable code is line 9. And again, this is using promises, but this is functioning just the way that all of our other JavaScript functions, right? Future data is an object, so we can use dot notation to invoke a method on that object and pass it the display function. We're not going to go into what dot then does in detail, but at a high level, what dot then does is take whatever argument you've passed it, whatever callback you've passed it, and store that callback in the onFulfilled property of the object. So what are we passing in? Passing in display, which is a function definition. And this will now be stored here. Okay, now let's move on to the next line of executable code. We have line 11, which is a synchronous function that we are invoking block for 300 milliseconds. So again, this is a function invocation. So what do we need to do? We need to open up a function level execution context in order to evaluate this function invocation. This is going to have a local execution context and a local memory. We're going to push this to the call stack and weave our thread of execution inside. And the contents of this function definition really don't matter. What matters is that it takes a long time. And so let's say while these 300 milliseconds are happening, while we're executing the code inside that function definition, the web browser threads, they get back our answer. And they know that the answer to this request that we've sent is the string Haya. So where does that go? That goes to the value property on our promise object. So value is no longer undefined. Value is the string Haya. What does that mean for our status property on this promise object? This is going to change from pending to fulfilled. And when something changes to, when the status property changes to fulfilled, what does that mean for the functionality that we've queued up in onFulfilled? It means display is going to be sent to the microtask queue. So let's do that. Display is sent to the microtask queue. And this whole time, as we have had something in our callback queue, the event loop behind the scenes is checking those same rules. Is the call stack empty? It is not, right? We have this synchronous function that is executing at the moment. So there's nothing that the event loop can do. We can't push anything onto the call stack because it's not empty. Let's say 300 milliseconds has finally passed and we are done with this long synchronous code. We can mark it as eligible for garbage collection. We can pop it off the call stack. We can weave the thread of execution back into global execution context. And at this point, when the event loop checks, is the call stack empty, it finds that it is. What's its second question? What's the next thing it's checking? Has all the synchronous code run? No, it hasn't. We just finished executing line 11. We still have line 15 to go. So let's execute that. We're going to console log me first. Okay, we've done that. The event loop checks, is the call stack empty? It is. Have we executed all of the synchronous code? We have. Is the microtask queue empty? It's not. So the first thing that we're going to do is push the functionality from the microtask queue onto the call stack. Okay, so our display function is moving on to the call stack. And what is the argument that we will pair with the parameter data here? The argument is the string Haya. Why is that? The string Haya is the argument to the display function because Haya is the value stored on the promise object. And so this happens automatically behind the scenes. The value of the promise object is what's going to be passed into whatever functionality that we have sent to onFulfilled, which in this case is display. So first of all, let's move our thread of execution into this, and let's make a little bit more space so that we can open this execution context in our diagram. Okay, I'm just gonna erase these extra lines here, and let's open display. So we have our local execution context for display, and we have our local memory. What is the first thing that we do? The first thing that we pair when we open up a local execution context, we're going to pair our parameters with our arguments. In this case, our parameter is data, and our argument is the string Haya. So when we move into the first line of this function definition, where we console log data, JavaScript knows that it should be console logging the string Haya. Awesome. We've run all the code that there is to run in this function. So we can mark it as eligible for garbage collection. We can pop it off the call stack, and we can weave the thread of execution back into the next stack frame on the call stack, which happens to be global. I'm going to make this a little bit smaller as well so that we have space for what's coming next. Okay, and what is coming next? Well, we have dequeued our display function. Our event loop is checking, has all of the synchronous code, or excuse me, is the call stack empty? It is. Has all of the synchronous code run? It has. Is the microtask queue empty? It is, which means finally, after many milliseconds later, we can push print hello onto the call stack. So let's do that. Print hello has been so patient. Let us invoke it. So we're invoking a function. The thread of execution is moving into this new execution context, and we need to open up an execution context in order to evaluate this. The first thing that we do when we open up an execution context is pair our parameters and arguments. There are no parameters or arguments to pair here. So we can move straight on into the first line. And what do we see? A console log of the string hello. So let's do that. Is there any code left to run in this execution context? No, there's not. We can mark it as eligible for garbage collection. We can pop it off the call stack. We can move our thread of execution back into the next frame on the call stack, which is global in this case. The event loop can rest. There is no code, there's no frames on the call stack. There is no synchronous code left to run. There's no functionality in the microtask queue, and there is no functionality in the callback queue. We have run all of the code. We are done here. Is this the order that you guessed when you made your guess when you first looked at the code? If not, why not? What was the gotcha that had you thinking it was going to be in a different order? Zoning in on that will be really, really helpful for cementing your understanding as to what we've looked at. Also, if you need to go back and rewatch this diagram or rewatch an earlier diagram, please do that. I cannot emphasize enough that there is a lot going on here, and we've added quite a bit to our regular diagramming to understand how this is working. Okay, so please continue to dive into this strategy. There's a couple things that I want to review before we wrap up. One is, what are the benefits of promises? I've already waxed poetic a little bit about this, but the semantics of promises are fantastic, right? We can use things like .then to be very explicit and make it easy to read about what we want to happen once we have our value for our promise object. We are going to fetch the first tweet, and then we are going to display it. We love this, right? There's a readable style. It's almost like pseudocode in a way. It also makes it look more synchronous. It looks like we are getting our data and then we are displaying it, even though we know the console logs, the order of things is going to be different. But it looks a little bit synchronous in the way that we read it. There is a fantastic error handling process. I'm not going to go into it now, but if you're interested, look up .catch as a partner to .then. And there is additional functionality that's been built on top of promises. So if you've ever used or heard of async await, async await uses promises under the hood. So this is another place where you could further expand your learning here. What are the problems with this? Well, really, it's just knowing the rules. How is the event loop working? How are things moved from different queues into the call stack? And what does that mean for how I can debug? So having a good understanding of how this works is going to really help you build code, write code that is easy to maintain, but also debug code easily and move through those technical interviews, which are sure to include asynchronicity as you go out there in your job search. I hope that this workshop was really helpful. Let's quickly review these rules before we wrap up. Okay, so we are going to hold any promise deferred functionality. This is any functionality that we pass into .then, like display, in the microtask queue, and a callback function in the task queue. You'll also hear this referred to as the callback queue. And this is so that we can coordinate along with the event loop when this is pushed to the call stack. We're only going to add functionality to the call stack when the call stack is empty and all of our synchronous code in global has run. And the event loop, which is checking every millisecond, if these two things are true, will then dequeue the microtask queue until it's empty, and only then dequeue the callback queue. Okay, so these are our rules. This is a great slide to snapshot, to keep next to your diagram as you're practicing, as you're writing your code, to figure out what order you expect things to happen in. This is really, really powerful. We've been using some simple examples because there's just so much complexity in terms of diving into how this works. But this enables a lot of complexity in terms of how we know and understand and expect the internet to function as we navigate it. This means that we can write synchronous code and deal or schedule asynchronous functionality, no matter how long it takes to fetch the tweet from Twitter, right? Or to load in photos or whatever it might be. So even though JavaScript is single-threaded, is synchronous, we are able to incorporate this otherwise unknown as we synchronize with external systems. It also means that we can write non-blocking code. We don't have to wait for that tweet to come back from Twitter in order to continue to run our synchronous code. And yeah, this is really, really what has enabled the web to be what it is today. I hope that this was really helpful and useful. I also hope that you will watch again, that you will come to one of our live workshops, that you will pair program with folks and connect with folks in CSX. What comes after this, I would really encourage you to take this conceptual understanding, regardless of whether you feel like you've got it yet or not, and apply it to some exercises on CSX or with a pair programming partner. There's nothing better than taking a conceptual understanding and teasing through it by implementing it and trying to implement it and seeing what goes as you expect and what goes differently. I want to thank you for sticking with me for this entire workshop, and I really hope to see you in another workshop again soon.